States for days. For any k greater than or equal to 1, let r sub k be the language of all strings x, where x is in 0, 1 star, and the kth symbol from the right of x is a 1. Show that any DFA that recognizes r sub k must have at least 2 to the k states. To get a better feel for this problem, let's consider what happens when k equals 1. In this case, r sub 1 is the language of all strings x and 0, 1 star, such that x ends in a 1. So strings such as 0, 0, 1 or 1, 1 would be in r sub 1, while strings such as 1, 0, 0 or the empty string would not be in r sub 1, as those strings don't end in 1. Now the main claim here is that any DFA that recognizes r sub 1 must have at least 2 states. Feel free to pause this video right now or take some time to think about why this might be true on an intuitive level. Okay, so what happens when we have a DFA with only one state? Well, it either has to reject all strings or it has to accept all strings. And this is not the behavior that we want, as we only want to accept the strings which end in a 1. So this DFA with only one state does not work. And more generally, the problem here is that all strings in r sub 1, as well as all strings not in r sub 1, end up at the same state, as we only have one state. We'll see how this sort of intuition translates beyond this example and can actually lead us to a solution to the more general problem. We're going to use two main tools in the solution to this proof. Those are contradiction and the pigeonhole principle. So these should be pretty familiar, as we use them a lot when we're proving that languages are irregular. The format of such a proof might look something like, assume for the sake of contradiction that our language is regular. This implies the existence of some DFA which recognizes the language, and this DFA also has a finite number of states, which we'll denote by k. Then we'll try to find a set of at least k plus 1 strings, and we want to use the pigeonhole principle on this set. Specifically, the pigeons in this case are the strings in the set, the holes in this case are the states of our DFA. Since we have strictly more strings than states in our DFA, we're guaranteed that some 2 of the strings will end up at the same state. So the concept of an ending state in this case is if we have some string x, we look at the transitions for each character in x, and the ending state is where we end up at in our DFA. So the pigeonhole principle guarantees that we will have some 2 strings in this set which have the same ending state. Then what we'll try to do is we'll try to derive some sort of contradiction using those 2 strings, which have the same ending state. We'll structure our proof to this problem in a very similar way. Initially, we'll assume for the sake of contradiction that some accepting DFA exists with strictly less than 2 to the k states. When k equals 1, so in the initial example we went over, this was the DFA that had exactly one state. Then we'll try to find a set of at least 2 to the k strings. And we want to use the pigeonhole principle on these strings. So our pigeons are the 2 to the k strings, our holes will be the states of our accepting DFA. Finally, we'll try to find some contradiction using those 2 strings which have the same ending state. Also, it's important to note that k in this case is some arbitrary number greater than or equal to 1. We're not restricting ourselves to the case where it's just equal to 1, like we did when we were initially analyzing the problem to see what sort of intuition we could gain. Okay, so again, we're assuming for the sake of contradiction, we have some sort of accepting DFA with less than 2 to the k states. Now we want to find a set of at least 2 to the k strings. Right now is a good time to pause the video to think about what sort of set we would want to use. Okay, one set we can use is a set of binary strings of length k. We'll denote this set as b sub k. Now, the choice of b sub k here is motivated by several factors. For example, this problem itself is about binary strings. Also, the cardinality of b sub k is 2 to the k because we have exactly 2 choices for each one of the k characters. It can be 0 or it can be 1. So b sub k will have exactly 2 to the k strings in it, and it's pretty closely related to the strings in our problem, so it's a natural choice. So now we want to see how we're going to use the pigeonhole principle. Again, the pigeons in this case are the strings in b sub k. The holes in this case are the states in our DFA. Since we have strictly more pigeons than holes, since we have strictly more strings than states, we're guaranteed that some two of the strings will end up in the same ending state. Visually, we can sort of see what happens. So maybe the first pigeon, the first string, it will have some random ending state. And the second string can have some random other ending state, and so on and so forth. But since we have more strings than states, at some point, two of the strings will have the same ending state. So let's call those two strings string x and string y. So we can see that they will have the same ending state, and now we want to derive some sort of contradiction using x and y. To do the contradiction proof, we're going to look more carefully at how x and y are exactly different. So remember, x and y are length k binary strings. We also know they're distinct, but they have the same ending state. Since they're of the same length, but they're distinct, this means that we have to have at least one different character among x and y. And what we're going to do is we're going to look at the first instance of such a character. So if this happens at index I, then we know that the characters x0 are equal to the characters y0, as are x1 and y1, x2 and y2, all the way up to xi minus 1 and yi minus 1. But at index I, we know that xi will not be equal to yi. Beyond this point, we don't really know what happens, but also we don't really care. So now the key question is, how exactly do we exploit the fact that we now know that index I is the first instance where x and y differ? And there's one important piece of information about the problem that we haven't really used yet. And this is related to the definition of when a string is in R sub k, and equivalently, when a string is accepted by a DFA that recognizes R sub k. So specifically, we know that a string is in R sub k if k characters from the right, we see that the character 1 shows up. And this is the same condition for which a string is accepted by the DFA that recognizes R sub k. So we want to use this condition somehow. And we can also notice right now that in string x, we have that x sub I is the k minus ith character from the right. And similarly, in string y sub I is the k minus ith character from the right as well. But we want to be concerned about the characters which are exactly k from the right. And this motivates the next idea, which is to consider these strings x prime and y prime. So x prime will be x with exactly I zeros appended to the right of x. And the reason we do this is because this now makes x sub I exactly the kth character from the right, which means that we can now actually consider whether it should be accepted by the DFA or not. Similarly, y prime will be y with I zeros appended to the right of it. And again, we can see that y sub I is the kth symbol from the right in y prime. And actually computing that it's the kth symbol is just a little bit of arithmetic. We're almost ready to finish our contradiction proof. As a quick recap, x and y are distinct length k binary strings. The strings themselves are different, but the ending states within the DFA are the same. Since they're of the same length and are different strings, they have at least one character that are different. Specifically, we denote the first such character as x sub I in string x and y sub I in string y. And finally, x prime and y prime are just x and y with I zeros appended to the right of them. The reason we define them are because they have the convenient property that x sub I is k characters from the right of x prime, and y sub I is k characters from the right of y prime. We need one more observation to finish, and this observation is going to be about the ending state of x prime and y prime. The reason we care about the ending state of those two strings is because we want to use this property about xi and yi being k characters from the right. So specifically, this observation is going to be that since x and y end in the same state, we claim that this implies that x prime and y prime also end in the same state. Visually, what this looks like is, this will be the ending state of x and y. So again, this is, since they end in the same state, this is just one state within our DFA. Again, this means also that after we've read in all the characters of x, we end up at the same state, and after we read in all the characters of y, we end up at the same state. Now, if we want to look at what the ending state of x prime is, we start from here and then we just see what happens after we read in I zeros. Similarly, to see what the ending state of y prime is, we start from here and then we just see where we end up at after we read in I zeros. So if we just do this process, we see that we'll always be at the same place for x prime and y prime. So after the first zero, we'll end up at this state, second zero, this state, so on and so forth. After we read in all I zeros, we'll end up at some state q. And this will be the same ending state for x prime and y prime. As a quick summary of the main ideas in this proof, it's just that x and y end in the same state, which we know by the pigeonhole principle. We append the exact same string to them, and this is how we construct x prime and y prime, so we can conclude that x prime and y prime also have the same ending state q. Finally, we're ready to finish. Remember, x sub I is not equal to y sub I. Also, we know that x prime and y prime end at this state q. And finally, we know that x sub I and y sub I are both k characters from the right of x prime and y prime respectively. We're going to have two cases to consider. In the first case, it's when q is an accepting state. So remember, in an accepting state, all the strings which have this state as an end state are accepted by the DFA. But the thing is, since xi is not equal to yi, we know that either xi is 0 or yi is 0. So remember, xi not equal to yi rules out where they're both equal to 1 or they're both equal to 0. So we have to have exactly one is equal to 1 and exactly one of them is equal to 0. So either xi is 0 or yi is 0. So without loss of generality, suppose xi is equal to 0 in this case. But the thing is, at this point we know that x prime has ending state of q. xi is equal to 0, and also xi is the kth character from the right of x prime. So this is a direct contradiction, because since q is an accepting state, we should have xi equal to 1. But xi is actually equal to 0 in this case. And again, we did without loss of generality. The exact same argument holds if we supposed that yi equals 0. Again, in y prime, yi is k characters from the right. It's equal to 0. But q is an accepting state, which means that yi should be equal to 1, so we have our desired contradiction. We essentially do the same argument in the second case, where q is a rejecting state. So in this case, we again note that either xi equals 1 or yi equals 1. So without loss of generality, suppose xi was equal to 1 in this case. Since q is a rejecting state, we look at the kth character from the right of x prime. In a rejecting state, this character should be a 0, but by our without loss of generality assumption, it's a 1, so this is a contradiction. Again, the same argument holds if we assume it was for yi equal to 1. In the string y prime, q is its ending state, it's also a rejecting state. The kth character from the right of y prime is y sub I. And if we assume that it was equal to 1, this is a contradiction because this is a rejecting state, so it should be actually equal to 0. So in both of these two cases, we see that we reach a contradiction. And these are exhaustive cases, so we can't really have anything else that happens. So we can conclude that our proof is complete. As a very quick high-level overview, essentially what we're doing here is we're constructing these two strings, x prime and y prime. We construct them in a way that guarantees that the kth character from the right is different in these two strings. We also show that these two strings have the same ending state. This is problematic because if the ending state is accepting, since the kth characters from the right are different, one of them will be 0 and this is a contradiction. Similarly, if the ending state is rejecting, the kth character from the right in these two strings, one of them will be 1 and this is also problematic. And this is how we reach our contradiction and we're able to conclude. Finally, let's go over a summary of the main methods and steps of our proof. So the main methods we used were contradiction and the pigeonhole principle. Again, this is pretty similar to some of the irregularity proofs we've done before. The structure of this proof is also quite similar. So the first step is, again, we're abstracting that there exists some accepting DFA of r sub k with strictly less than 2 to the k states. Then we found a set of exactly 2 to the k strings, and we called this b sub k, and it's simply just that the set of all binary strings of length k. Using this set of strings, we're able to invoke the pigeonhole principle. So our pigeons in this case are the 2 to the k strings, so b sub k. Our holes in this case are the states of the DFA, and we have strictly less than 2 to the k of those. Since we have more strings than states, by the pigeonhole principle, we are guaranteed that some 2 strings map to the same state. In other words, some 2 strings x and y have the same ending state. Then we constructed these strings x prime and y prime from x and y. X prime and y prime are simply x with I zeros appended to it and y with I zeros appended to it, where I is the first index where they have a different character. The purpose of constructing x prime and y prime is that this differing character occurs exactly k characters from the right of their endpoints. Finally, we are able to complete the contradiction argument as x prime and y prime have the same ending state, but the character k characters from the right of them is different. So if the ending state was an accepting ending state, we would have one of x prime and y prime, the kth character from the right, would be a 0, and that's a contradiction. Similarly, if we had a rejecting ending state, the kth character from the right for one of x prime and y prime would be a 1, and that's also a contradiction. So in either case, we have a contradiction.